I'm Andreas, Andreou. I'm going to be giving you the second talk today. Munia, who talked before, she's a boss, so she decided what I should be talking. She gave me a title. I was thinking about it, and I decided that this is probably a tentative title for the presentation this morning, but it may change. And I will put the presentation on the website, and I will put some papers, but you're going to have to give me about a week to really add a few things I really wanted to, since I dove into this and I decided to really, I want to do a more thorough job, especially in kind of painting a more broader landscape of what's going on. So this is really, the outline for my talk. There will be a brief introduction, and then I will just have 2 or 3 slides on production and auditory system. I think Munia talked probably at your heart's content about the auditory system. And I know next week you're going to have a whole day on production, voice production, vocal tract, and apparatus, and all that. So, but I thought it would be good to have something here to really tie things together. Then I will talk a little bit about some of the perceptual attributes of speech and sound. Again, this is not going to be a thorough discussion of everything about auditory perceptual psychophysics, but rather some simple examples, to really demonstrate the ideas and the principles that I want to carry on in the talk. Then I will talk a little bit about applications of these perceptual laws or ideas into telephony and hearing aids, and then I will conclude my talk using, again, some ideas from automatic speech recognition, ASR. There will be not much math. There will be a few equations. Again, if you really want to find the math, there is papers there to find the math. But again, the discussion here is meant to be more of an intuitive nature and more of an introductory nature, so everybody can follow. So let's talk about speech technologies. Well, there is basically two classes of speech technologies that one is engineering today. And the first class is that deals with basically precise restitution of information, and that is telephony. You want to talk to someone on the phone. When the other person hears you, you want to really know that John called or Jane called and not Jim. You don't want to hear someone else's voice, even though the message would be the same. Hearing aids. If you have a problem with hearing, you want to hear the world the way it is, not in some abstracted version of the world. And also music. I didn't include music here, the same thing, because a lot of work has actually it's been done that links perceptual psychophysics of music and music coding technology. If you have an MP3 player, you're using that. I mean, it's in there. It's been there forever. This is key in being able to really encode faithfully sound in a compact space. So, and by the way, and the way it works, it's because the music coders cheat you. There's certain things you cannot hear, and they know about that, so they don't really give you that information, and you think you hear everything. So remember, this is the first category, and that would be related to precise restitution information. And the second category, that's related to, by the way, speech synthesis is also belongs in the first category. You really want to reproduce speech in a faithful way that is pleasing and so on. The second category, where the ideas that we'll be discussing today, and you've heard this morning from Munia, is relevant, is what I call information extraction from speech, and that is automatic speech recognition and automatic speaker identification. You know, what you really care is not really about speech per se or voice, but rather something about the speech, something about the voice that is relevant for solving a task. Okay? So remember this: two different categories, broad categories of technologies, and many things that you do for one not necessarily translate to the other. In fact, actually, you may have the intuition that, hey, because this guy did this in coding, I'm going to use it to do speech recognition. Oh, it doesn't work, okay? And many years have been spent, especially in AT&T, which were really focusing on the first, in trying things for automatic speech recognition that really didn't quite work. They have incredible systems now, you know, but it took them a while to figure this out. So the question here, which I should be able to ask before we go on, otherwise we're wasting our time, and if I don't give you a satisfactory answer, raise your hand right away and we can change the discussion. Why is auditory perception and/or physiology relevant to speech technologies? The answer is not obvious, but let's argue, so to speak. Well, in telephony, hearing aids, etc., the ultimate consumer is a human, and hence taking account how humans hear makes sense. Okay? You buy this? Who doesn't buy this? Okay, it's sensible. I won't argue with that, and probably you couldn't really argue too much with that, given that the market today has told us that this is happening, and so, you know, market speaks, money speaks when it comes to technology. The second aspect, you know, going to the second category, in automatic speech recognition or information extraction systems, the performance and especially robustness of machines does not match that of humans, and hence understanding the way humans process speech may help the engineering of more robust machines that extract information from speech. And by the way, this is kind of the holy grail of speech recognition, robust speech recognition. You're here because we have CLSP, the Center for Language Speech Processing. I founded CLSP 15 years ago, and this is really essentially what we told the sponsors 15 years ago. We really want to understand how humans do it, how to improve robustness. Well, guess what? 20 years later, or 17 years later, we have a new center, and that's exactly still the problem we're trying to solve. You know, how do you do robust speech recognition? How do you make machines be robust as humans? And that's, it's really that's a shaky, topic, because maybe 15 years ago, I would have given a different talk than I'm going to give today. But I think there is something there. And I have to admit, Fred Jelinek, which is the director, our fearless leader here, has influenced quite a bit the way I think about this problem. So this is my one single slide on the organs of speech and hearing. You have the this is from Maureen Stone's lab. She's going to be here with us a couple times. I have to get back to her. She's at the University of Maryland. She's collected a lot of data on production, how the vocal apparatus of human vocal apparatus works, and modeling. This is a vocal tract. You have somewhere here, you have your glottis, you have your lips, you have your tongue, and the physical configuration of the vocal of the jaws, the tongue, the lips, creates a cavity, and that cavity really is driven by the excitation of the glottis, creates the sounds. The sounds propagate, they come to your ear, and on we go to all kinds of things that Munia talked about. You have a cochlea, you have a mechanical to electrical converter somewhere, and then you go to the brain, and the magic occurs in the brain that we're really trying to understand, and I'm sure you talked about that in your presentation. So let me actually, let me exit. I want to play you this little video. Okay, can you let me, if we can? Well, I guess it's as high as it gets. Let me see if I can make it a little bit louder. Oh yeah, I can. Oops, I turn it off. I press this. Okay, what you see here basically is this person. Can someone tell me what she says?
It ran a lot.
It ran a lot. What you see here in this movie, you can see the lips of the speaker. You can see an ultrasound cross-section of a sagittal view of the articulatory system. You can see the white. This thing here is the tongue, and you can see actually how this incredible machine, that you have in your mouth that doesn't even know. You don't even know that it moves like this, works, to produce and articulate and communicate with other species, okay? So let me go back to my presentation. Good. It's always good when your multimedia presentations work. Now, I don't know if Munia showed this, but let me take a second to describe what happens next, okay? So after you speak, ears, the sound waves come to your cochlea, and out of the cochlea you have the auditory nerves, and the way and the sound is encoded. So you have one input, sound input, and you have several thousand outputs, okay? And these several thousand outputs are the auditory nerve fibers. Did you talk about a little bit? Okay, so some of the early work here at Hopkins by Young, Eric Young, which is the Department of Biomedical Engineering, they really focus on recording sounds from the auditory nerve as from a cat. And tell me I'm not a cat. Yes, we're not cats, but our auditory system shares some similarity how cats behave, to synthetic sounds. And so now actually this gives me an opportunity to really kind of describe sounds in its prototypical components. What you see on top is the sound ba, ba, ba. And the way it's synthetic, and you can tell that it's synthetic from the waveform, a ba waveform, a natural ba waveform would be a little bit different. But what you see basically, sound can be described in terms of formants, F0, F1, F2, F3. And these formants are the resonances of the vocal tract of the machine that actually produces the sound, okay? And as you articulate ba, the formants, the resonances of your vocal tract change in time. This is really time in milliseconds, from 0 to 8 milliseconds. Change in time, and those are the various frequencies. And you can see now the formants have frequencies between 100 and 3,000 hertz. So as time goes on, those resonances change because the machine that creates those sounds change. And as they change, you see the resultant speech produce the speech pressure wave that is translated into an electrical wave that you actually see, electrical signal that you see on top of the panel, okay? Now, wouldn't it be interesting to know what's happening on the output of the cochlea, on these 3,000 wires that come on the output of the cochlea as you actually put the synthetic sound? And this is exactly what you see here. Ba, at 69 dB sound pressure level. As a function of time, this is about 80, I apologize about the bad figure. This is 80 milliseconds. And what you see, this is actually I cut and paste from our paper. We didn't create this figure, actually. I believe Secker Walker at MIT created, Shihab Sharma actually created figures like this. But what you plot here basically is time, and what you plot here is the instantaneous firing rate of the fibers. And for different fibers which have different best frequencies, and you can see now that different fibers, this group here, this group here, this group here, this group here, encode different formats of the different formats. I was confused. I was looking for what's going on here. This is upside down. This is lower frequency, higher frequency. So lower frequency scale goes from low to high. Let's just say, oh, it doesn't make sense. You know, they look like synchrony locking here. You know, but so what you see basically here is different fibers now encode the instantaneous frequency of different formats. So look at the inter-event on these peaks here. If you take 1/t of that, you're going to basically see that that encodes F0. And similarly, on a better picture, you see it better. I'm sorry, I can't show here. Another group of fibers encode F1. Another group of fibers encode F2. And what's happening, actually, they change in time. So as time goes on, different fibers encode different formats frequencies. So, aha, one says, this is great. We already got one clue of how to build machines that here. All we need is a machine that actually takes sound, produces, you know, a couple thousand outputs, each one encoding, dynamically reconfigured to encode the sound, and we are in good business, and so we did. Isn't this beautiful? Now, this is beautiful because this is really artificially created data. This is actually the same data, but I can make the point, plotted in the same way. Now you can see how nice the clean data is, because this is not created by a CAD, but this is created by a silicon model. We actually built a chip that actually had the whole cochlear filter bank, the hair cell model. We didn't have, of course, a few thousand fibers. We only had, I believe, something like 90 or something. So, and you can see, though, that our model actually replicates the phenomena that we actually see in biology. This is work that I did with Roy-Min and Moise a while back. That was 1992. That's 15 years ago. Wow. So now you should ask me now, so what? Well, you know, you haven't told us anything yet. Why should I, by replicating that, what does it help me in making a better machine? Well, it's true, actually. It doesn't help you in making a better machine, but actually, if I do want to build a hearing aid, and even if I were to build an acoustic front end, I would probably use something like that, because that representation of sound is a sensible representation to use, okay? We're going to revisit the theme, you know, representation, and how do you find the best representation, okay? So that representation in a hearing aid, what I would call a cochlear representation, and this is something that comes from biology, from neuroscience, from people like Munia and Shihab, her advisor, and Eric Young down in the medical school. Now, let's switch gears now to the other side of the coin, and someone stands up and say, well, you know, but I'm a psychologist, you know, I'm a cognitive neuroscientist, I'm a perception person, you know, who cares about how the brain does things? At the end, all you really care is how do we perceive things, okay? How do we, you know, you have the coglia, you have the brain, and at some point you perceive something. That's really what you care about. Well, let's try to follow that path now. Let's try to follow the path of abstracting from perceptual studies. And this is actually not a new idea. This is by no means a complete list of perceptual attributes, but it's actually, I'm describing here three key, and Munia probably will agree, this is really among the most important perceptual attributes of sound, which is loudness, pitch, and timbre. Loudness is a perceived intensity. Pitch is a perceived fundamental frequency or tone, and timbre is a perceived something, which is a little bit more difficult to describe. Basically, it's a perceived quality of sound that tells you the difference between a violin and a viola, or a wind and a flute and a oboe, and so on. And also, between, to a certain extent, people voice. I mean, different voices have different timbre. I mean, a few times in my life, people have come to me and say, well, do you work for a radio? Are you an announcer? I mean, you have a voice that has a quality. I say, well, I don't know. No, I'm just a normal person. So let's actually talk a little bit about those. What's going to happen? One of these days, I'm going to go and see the video from my lecture. I'm going to say, oh my God, what did I do? Okay, so what is loudness? So loudness, as I pointed out earlier, is a perceptual correlate of sound intensity. And when you see the Wikipedia symbol on the right, that means that I stole this from Wikipedia. Wikipedia is a great place to find things, but make sure you double check your sources. It's subjective, and it varies from person to person. And it is a function of sound duration. And this is really important. In other words, the way we perceive sound, okay, depends on how loud is the sound. It depends on how long the sound has been impinging on our ears, okay? So that is something that you have to remember. And in general, this is really our sensitivity to sound. Humans have a sensitivity to sound highest sensitivity in these middle frequencies between 100 and 5,000 hertz, and then at low frequencies we don't have, we are not as good as, we are not hearing things as loud as they are actually, okay? And that has to actually do with our system, our physiology. Even though we can all agree that we all have different loudness scales, I will call this a loudness scale, a scale that describes the perceptual sensitivity to sound intensity. There is actually an ISO. There's actually a standard for loudness scales. And the reason there's a standard for loudness scales is because at some point manufacturers have to make devices, microphones, whatever they make, and they actually employ these loudness scales in the specifications of their devices, okay? So there's actually a standard that defines a loudness scale, even though it changes from person to person. Now, as I said, I think once you start talking about measure intensities, it's always a good idea to actually go and put some figures to get an idea of what this means. So there is 2 units for loudness, the son and the phone, and the correspondence between the son and the phone is given on this little table here. So for very loud things that are really painfully loud, you have the sound pressure level reference to 2 micropascal. Pascal is force per area, is pressure on your eardrum. It's basically 676. If you are near a jackhammer 1 meter away or in a disco, it's about 60. You only a factor of 10 zones beyond the threshold of pain. Sometimes, actually, even if you're in a disco, it's very painful. So it depends where you are. Again, if you go near a car, that's about 4 to 16. So that gives you an idea of where loudness is in an absolute scale. And point to be made, actually, the 0 zones is a threshold of hearing. Okay, so it is a relative scale. It's a relative scale, it's a logarithmic scale, where 0 is really the threshold of hearing, and you actually go levels above that for different loud intensity, for different intensities shown here. Now, Another scale now, another law or another scale, which I would like to talk about, is the Mel scale. That's another psychophysical scale, and it's a measure of pitch. You know, it is really a psychophysical scale that gives you a perceptual feeling for frequency or the tone. And Mel was actually conceived, was defined by Stevens and Volkmann in 1940, basically trying to relate the absolute measurement of frequency to the perceptual measurement of frequency, which what we would call tone. Okay, so this is really about 40 years ago, 45 years ago, and then they chose a reference frequency of 1,000 hertz and designated as 1,000 mels. So it is again, it's a logarithmic scale. So you really you need to define a point in this scale. And then what you're going to see now, listeners were presented a signal and asked to change its frequency until the pitch they perceived was twice the reference, then 10 times the reference, and so on. And in this case, they actually created this psychophysical scale. And from this data, the Mel scale was constructed. Mel scale actually maps frequency to Mel linearly below 1 kilohertz, and then it has a logarithmic dependence. And basically, here is the Mel scale. The formula for the Mel, the frequency in Mels, is given by this formula here. And as you see, it's a logarithmic formula that has a pivot point about 1,000 kilohertz, which is really the reference point where it was done. And what you should think about here is when we talk about Mel scale, the way you should think about it is that think about frequency bands of equal width, and think of it as how many for lower frequency, this much of delta F frequency difference in the real scale corresponds to equal amount of frequency in the Mel scale. But as you go to higher frequencies, in order to get the same delta F in the Mel scale, you're going to have to span bigger range of frequencies. Your delta F in the real frequency is going to be bigger, which basically tells you that you really cannot tell the difference between 10,010 and 10,020 or 9,990, okay? You cannot tell those differences. They are grouped together in a bin, and that bin is kind of the unit bin for a Mel, okay? Clear? Okay. So let's now move to, we've talked about physiology, we talked about perception. Let's talk a little bit about some of these ideas and how they play a role in telephony. And basically, telephony is really people talking to each other through wires or wireless connections. And essentially, the goal of telephony and the goal of speech processing or applying any of these ideas to speech technology in telephony is to really compress the data. You have someone speaking. You need to send the data through some wires to the other side of the United States or across the Atlantic through a fiber optic. And then someone is going to pick up the phone and you're going to talk to that person. Now, it used to be that sending data next door, as opposed to sending data across the world, it was much less expensive. In other words, it was way more expensive to send data across the world than to send data next door, and therefore you needed to have a way of taking your speech, and compressing it, making it more parsimonious, so to speak, without losing any of the characteristics that you want so that you can actually ship it across the world. Today, that's no more true, okay? Whether you go to a FIDI and you send the data across to your neighbor or across the world, the cost is more or less the same, okay? Because of the fiber technology. Still, this is relevant because now you do other things. So essentially, you have what is known as the encoder and the decoder. The message there is going to be the phone call, talking to your friend, and then you're gonna, this is a canonical model of a communication system. You're gonna invoke all kinds of coding processes, typically in two general classes. You're gonna do some channel coding that is gonna take care of the fact that your signal goes through this noisy channel, these wires under the water, you hear the waves, and really takes care of that. It doesn't get, it alleviates some of the noise, it alleviates some of the issues with noise and distortions in the system. And then, in general, you're gonna have two coders, a coder and decoder, which is gonna basically say the following: aha, if I know something about voice or speech, I should be able to use that a priori knowledge, okay, to help me reduce the amount of data that I'm going to transmit, okay, and that is actually in general called source coding, okay. So use some prior knowledge about your source, you know, to reduce the data rate, so that you can actually send more people, you can put more people on the line. The first idea actually that actually evolve out of these wire lines is that of a Mueller codex, standing for coders and decoders, and basically it's a time amplitude coding that actually matches human loudness perception. There you go, the loudness perception. We talk about perception now. People, what does it mean? Well, basically we are really good at hearing very, very, very weak, very, very low-level sounds, and we don't really care too much between the differences of very loud sounds. So if we look at the waveform, it makes sense to put more resources to quantize, to allocate more resources in the low levels of your sound than in the high levels of the sound. This is really kind of a borrowing from the loudness scale. That's what you hear. And so we have basically the what is known as the Mueller codec law, and the inverse of that, f-1, which is really the decoder. And if I were actually to say, well, is this justified? Yeah, actually it's justified. And I mean, I just say, well, you know, I mean, sound, voice, and speech has a lot of low level, it has a lot of signal around zero. It's more probable to find your signal around zero than at excursions away from zero. So basically, what we did here, we took actually timid database, and we took all the data and we plotted the distribution of the data, probability normalized to the amplitude of the data. So basically, you take the waveform and you say, well, you know, what is the probability of finding a waveform whose value is 1 volt, 1.1 volt, 1.2 volts. We normalize the amplitude to standard deviation of the signal, plotted in the X scale. And what you see actually, indeed, you're finding out that indeed, most of the speech signals peak are highly probable near zero, near the low levels. Actually, the probability that fits this data is a double gamma probability, and what you see here, X is data, continuous line is parameter A 0.5, 0.267, and continuous line parameter 0.5. So actually, I didn't really, if I were to go back and I didn't know anything about the loudness scale, I say, well, if I want to solve this problem, let's go and collect some statistics, see what the signal is all about, and from the signal, let's go and design our codec. And that's actually, this is kind of going to be the recurring theme, you know, in my presentation. Actually, in retrospect, we really didn't really care too much about loudness. even though it was kind of an interesting thing. Don't, you know, I mean, but it's there, okay? So, and it has motivated us to actually go and do that. But by going back and looking at the data, we can figure out the same thing, okay? So this is really key. So Mueller codecs basically have this form. The horizontal axis is 255 levels, 8 bits. The vertical axis is 16 bits, 65,000 levels. And basically what you see here is that you put more bits at low levels than at high levels, and you don't really quantize very often the high levels. These codecs, in the old days when we didn't have digital signal processing, these codecs were done in analog. Nowadays, these codecs are, this law is actually built in the A to D converters that actually quantize speech, so it's actually part of the system. Okay, so, and this is again, you know, the input-output relationship of a box that actually does Mueller coding. On the x-axis is the input. On the y-axis is the Mueller quantizer. And again, if I had a linear quantizer, that would be the green line. The Mueller codec is the red line. And Mueller is used in US and Japan. And in Europe, they have something else. They call it ALO, which is similar to the Mueller coding, but with some slightly different. But essentially does the same thing, where you're putting more resources, in this case, bits, in the lower values of your signal than in the higher values of your signal, okay? Now, I think I'm one of the statistics guys. You know, I mean, likes to look at the statistics and signals and figure out what can you do with that. So another interesting question now is the following. Let me look at the frequency distribution, okay? The power spectrum of speech signal, okay? So again, we took TIMIT and we computed for the whole database the power spectrum of TIMIT. And don't worry about this. Don't worry about this part of the spectrum. Start worrying from about here, which is about 200 hertz, to about 4 kilohertz. This is actually where actually a lot of the speech sounds are, the formant frequencies are. What do you see there? Well, I see basically a 1 over f law, okay? If I look at the distribution of frequencies, it follows 1 over f to some power a law, much like actually you see in many other natural signals, you know, in the vision, many the zero crossings follow 1 over f law, and so on. So now, let me take this and see if I can go backwards now. If I want to, let me give you the following problem. You have that frequency distribution, and I have one wire that carries your signal, and I want to split my signal now into 100 wires, okay? Let me pose the following question. How should you design your splitter? How should you allocate frequencies in these 100 wires, okay, to optimally, and I will define optimally now, to optimally split the signal. Optimally, I will qualify as, in an information theoretic viewpoint, putting equal amount of information in every channel, okay? So I have one wire, and I want to make 100 wires, and I want to put equal amount of information in every wire so that if any of the wires dies, it doesn't cost me much, okay? It's a good idea. So turns out, actually, you can solve that problem, and we solve that problem, and you can make a filter bank that would actually solve this problem, where it puts equal amount of signal power in each channel. And basically, the solution to this problem is a filter bank that is a constant Q filter bank. In other words, no matter what frequency you go, your Q of your filter stays the same, okay? So, or, conversely said, it's a filter bank where if I plot the filters in a logarithmic scale, that is my x scale, look at the top plot, all filters look the same on this scale. However, actually, if you plot them in a linear scale, they're not going to look the same because they're going to have different bandwidth depending on the frequency they are. Aha. Well, this is interesting. Again, now I went and I look at my signal. I look at my signal statistics now, and I produce a coder or a coding principle that says now, if you have one and you want to split in 10 channels, make a filter bank that actually has that form. Have you seen this earlier today in Munia's presentation? Well, so now Munia comes in the room now and says, oh, gee, look at that filter bank. It looks like a cochlear filter bank. Aha, I say. That's interesting. So now I can hypothesize now that if this is what the cochlea, if the cochlear filter band looks like this, is actually has filters on a constant Q filters, then I can hypothesize, I can actually speculate now that the role of the cochlea is to actually take the speech, and put equal power in each one of the end channels, so distribute equally the power in the speech signal. So the reason I actually bring this, and this is actually very important if you're designing hearing aids, this is actually a framework. It's an engineering framework that actually we devised to actually design filter banks for hearing aids, devices that uses hearing aids. So what is interesting now is that we can see the human physiology, we can see the rigorous engineering principles such as information theory and signal processing kind of play in a feedback loop now where one supports the other and so on, okay? So the message that you're going to take home today from my talk is really data is everything. Okay, and let me go to the next topic now. Andrew, how much time I have, please? Half hour, okay. Let's talk a little bit about automatic speech recognition. You really want a person. You go and buy, naturally speaking, this is from what used to be Dragon Systems, and the creator of that system is actually here. You may bump on him. You know, this is Jim Baker. You see him around the workshop. You know, so if you see him around, say hi. Of course, his company is sold now, and Nuance has the product. But the idea basically is you want a person, and you want to talk to the computer, goes and buys the package, and you want the computer to type what you're speaking, and actually the guy is talking is saying, imagine if you could talk naturally to a computer without a wearing headset. The point to be made here is that there is no speech recognition system out there for transcription that actually works without a specific headset tailored to that system. And that's actually one of these key issues, you know. The reason it doesn't work is not robust, okay? You need a very specific headset to match the models that they have trained the system with. So this is really an issue. Now, I have some cartoon figures here that are going to help me carry through, and there's going to be a little bit of math on the bottom just to really tie to things that maybe you'll be doing in the workshop if you'll be doing some machine learning and things that you'll be seeing, or probably you've seen yesterday or tomorrow or whatever. In general, a machine, a speech recognition system, actually think of it as two machines, okay, with some knowledge. There's a machine actually that acquires the knowledge, okay? I'm going to define that machine ML, learning machine, and I'm going to acquire the knowledge K raw. Think of K as the knowledge, as the structure of the knowledge, and raw as parameters. So the knowledge can have parameters where raw is the parameters. Think of it as a model, a specific model, or something, you know. And raw is the parameters of the model. And in general, you have some input data X, some input data Y, maybe speech sound on the left and words on the transcription on the right. And what you want to compute the arc max, the probability of X comma Y, and create the models K-raw. Okay, creating the models K-raw is really making the machine learn the relationship or between X and Y. Okay, then when the machine is operating, the knowledge now will come to bear on the machine now, and now you have X, you want to compute some estimate of Y, given some knowledge K-raw. K is the models, raw is the parameters of the model, and so then you want to maximize the probability of X, K-raw for all Y's, Y, Y1, Y2, Ym, okay? So this is really the prototypical models that you'll be working here. If you're doing speech recognition or machine learning, you have a machine that learns, and then you use the machine in the evaluation mode now, computing what you've learned and really testing the machine with in a given situation. In general, for speech recognition, the machine actually has 3 components. It has a transaction actuation component. This is general, where actually, so to speak, the front end, you don't worry about this. In this case, that would be an adaptive microphone, able to work better than the microphones that you get with naturally speaking, for example. It would be a component that has feature extraction, and then it would be a component that does the classification. Again, for each one of these components, there will be a machine that actually does the work or learns knowledge relates to feature extraction or knowledge relates to classification. You know, your classification, your feature extraction maybe is you learn a filter bank from data, and classification, you learn some phone models for your speech recognition. You know, this is your knowledge and the machines, and you're using HMMs and the EM algorithms to actually train your machine. So I guess this is a shorter talk than I thought it is. Let's now focus on a problem that I worked on a few years ago. That was 1994. In a workshop like this, it was before the workshop came at Hopkins. That was the last workshop at Cape. So can we make a machine now that incorporates knowledge from speech production, in other words, vocal tract apparatus, okay, and to improve speech recognition? That term is missing there. We're talking about speech recognition. And can we make a machine now that can actually learn from data the parametric variability in speaker groups, okay? Again, if I come and ask you the question, can we make a machine that actually can learn incorporate knowledge from the vocal tract apparatus of a speaker, you're going to tell me, well, that machine will only work well for him and not for him, because that machine is going to learn his vocal tract and not his vocal tract. I don't want that. So I want to be able to build a machine that incorporates the knowledge, but at the same time, I want the machine to learn how to extract the model or to find a parameter space which is really invariant to the speaker, okay? Or I should say, it's invariant to a class of speakers, you know. So at least the machine can say, oh, yeah, this is class A, tweak the knob here. This is speaker B, tweak the knob here, and so on, okay? And one of the obvious things that you may think the machine will find is if you have children, adults, and women, and male, and male and female, it will find classes that are the speakers for children, males and females, because they will roughly have different vocal tract lengths, okay? Now, actually, this is, if you're in the business, who is doing automatic speech recognition here? Who is doing anything that has to do with ASR? Okay. This is actually known now as vocal tract normalization. It's an idea that has given dramatic results, okay? and as I said, this is something we did about 1994 in a workshop like this. I was a student there. I mean, I was a professor, but I was a student like you, working with other people like you. And all of a sudden, we found ourselves solving this incredible problem, that actually make a big impact in the way actually speech recognition works today. And what is the idea? So the basic hypothesis, so what is the theme of my talk today? Are there any ideas from psychophysics, from perception, from physiology that can actually come to bear to solve problems in technology? And technology, telephony, speech recognition, okay? And the recurrent theme, it has been that yes, maybe, but we really have to do a good job in really looking at the data, because one solution doesn't fit all sizes, so to speak. So the basic hypothesis here in pursuing this idea is that if you can a priori account explicitly for known sources of variability, then you probably could do better performance. You could do better, okay? Anytime you use prior knowledge about your problem, you're always going to do better, okay? Now, I don't know what the length of your vocal tract is, and I don't know what the length of your vocal tract is, and I don't even know whether the length actually correlates with your height, actually. I mean, or your weight. Actually, when we first proposed this, the guys were making fun of us. They said, well, the length is proportional to the color of the hair and the eyes, I mean, because it is really not something that you really know. You need to find out. We know, though, that the vocal tract varies from speaker to speaker, and this is a source of variability that if we could account it during training and put it part of the HMM models, could yield improvements. Originally, before that, there was work by Wakita and Neuberg where they thought that if you can normalize the vowels of speakers by changing, by imagining that you can actually incorporate knowledge from the vocal tract. So that's a hint, actually, that something may be doable here. And why? Because the vowels, the formants of the vowels are the resonance of the vocal tract, and in principle, you will think that your HMM models will capture something about formant places in the frequency bands and so on. So there is something there that is a hint that this may work. So I'll skip the details, although I will because it looks like I'm running out of time. But I will give you now a prototypical model of a speech recognition system. In general, what you hear, what you give the machine is a speech waveform. That speech waveform comes as a result of my brain trying to say something, the muscles in my vocal apparatus almost doing a good job in conveying what my brain wants to say, okay? And then you propagate through the environment, it comes to the microphone. That's the channel. Everything between my brain and the acoustic processor, I will call it channel. The encoder is my brain. You look at the speech waveform as a function of t. The acoustic processor will take these observations and it will compute the word sequence for a given sequence of speech signals that is a likely sequence given a language model that will help me reduce the work that I have to do, okay? Now, so the first idea here, you go back to physics, and turns out physics deals with one-dimensional problems. Physicists like to really look at squares or spheres or rectangles. If I look at the vocal tract as a simple tube with closed one end, and I find the resonances of the tube, I find out actually that the end it has nodes which are inversely proportional to the length and proportional to the speed of sound, c, velocity of sound, which is about 353 meters per second. And so if I take this simple equation now and I say, what if now I change the length of the vocal tract by a fraction, nu, okay? Nu is 0.1, 0.2, 0.3. Then the resonances will change inversely proportional to nu. So actually, that will create now formants at different frequencies, which are going to be really proportional to nu. And let me actually demonstrate this in the following slide. This is plots of speech spectra. Has anybody shown you speech spectra, Munia? Yes, okay. So these are spectrograms. This is time, and this is frequency. And what you see here, basically, starting from top and going to the bottom, is the middle is unwarped, undistorted spectrum. The top spectrum is resampled to really create this dilation of the spectrum, this compression of the spectrum, and the bottom is resampled at 6 kilohertz to create a dilation of the spectrum. Essentially, this is 8. The ratio 8 to 6 is really how much we are dilating or compressing the spectrum. And you can see the various formants frequencies as a function of time. They moved up here. This is the original. They moved up here, and they were compressed down there. The vertical axis between 0 to 2 kilohertz, you can see the second formant there is about between 1500 and 2 kilohertz, while in the original representation, it was about 2 kilohertz. So this is interesting now. So only if I knew when I receive the sounds from you that the speaker falls in a class that has a nu of, let's say 8 nus. Okay, I'm gonna quantize my speaker space into eight-dimensional spaces. I'm gonna assign a nu, and if I knew where the speaker came from when I hear the sound, I will warp the spectrum to make the speaker fit that class and train my machine now given this data instead of the original data. Okay. Now, again, this is for you that will be doing experiments in the next 6 weeks. Don't try to solve the problem from scratch like this, okay? Because you never get anywhere. If you have a good idea and you know how to go about doing it, the first thing to do is cheat, okay? Pretend that you know what the data is, okay? Pretend that you know because you can go and compute it, okay? Pretend that you know what classes it is, okay? Go run the experiment, okay? And if you run the experiment and it works, then try to solve the problem, the real problem, without cheating, which is really not knowing a priori and computing that, which is a different problem altogether, okay? So again, for you, you're going to be working in the workshop here. If you have a good idea, go and solve a slightly different problem, what I would call a cheating problem, that will allow you to really demonstrate that your idea works, and then you can go full force after the workshop probably and work on the real problem. By the way, I should point out that we demonstrated this in July, this idea. By December of 1994, this was July of 1994, by December of 1994, Dragon Systems actually had this built in the code working. I mean, in the sense that they actually not only took the idea, but actually figured out how to do the practical aspects of it to make it work in a real environment. So I'm going to skip the details of how we did it and show you this graph here. And what this graph shows, basically, if we took the warpings and then when we did these cheating experiments, we had how many classes we had? 1, 2, 3, 4, 5, 6, 7. Oh, we had 16, I guess. 16 classes there, and we went and looked at the training data, and we discovered actually that there was a best warping for speakers in the training set that actually fell into two distributions. Guess what? There is males and females. You know, I mean, that is, we didn't put explicitly male, I mean, we didn't put explicitly here to find males and females. We actually found out actually that the recognizers work better in this, for certain speakers with this distribution, okay? So what do we describe, actually what we discovered here in retrospect, we discovered that the world actually can be described as far as speech production is concerned in two big groups, you know, and maybe one is females and the other is males, you know. I mean, that's really what basically this data tells you. But the point I'm trying to make is that this came as a byproduct of the experiment and not built in the system. If we were to build this in the system, actually, it wouldn't work as well, actually. So anyway, so this is really vocal tract normalization, and the key result to note is that basically we went for roughly 4622 to 5390 to 51, which is really 5% improvement on the switchboard. Actually, about 3 or 4 years ago, people look at the decade and they voted which is the biggest discovery that really advanced the state of the art. This actually was voted #1. Vocal tract normalization has made an enormous impact in the way speech recognition technology works. Now, how much time do I have, Andrew? 15 minutes, okay. Any questions so far? So let me now ask another question now. I hope I convince you that by taking hints from nature, from the way things work in biology, from our production apparatus, from the voice production system, and from our auditory perception, we can improve technology. Can we go one step further? Can we go to the psychology department and say, aha, Mel scale, Loudon scale, we will now design an experiment that will actually discover the optimal scale, perceptual scale. We'll make a machine now that will actually find this Mel scale from data, okay? Because we think that for the same reasons that humans use this perceptual ability to communicate between each other and exploit these perceptual laws, we believe that a machine should be able to do the same thing, okay? And if the machine should be able to do the same thing, and if that's the goal of the machine, okay, if we make a reasonable goal of the machine, then we will go, and if we do a lot of experiments, and if we had evolution running fast on Spark workstations, you know, and trying all kinds of different experiments, we should be able eventually to come to something which is really relates to these perceptual laws that you actually guys found empirically from psychophysical experiment. I'm not really knocking off perceptual psychophysics here. I mean, I think it's wonderful, actually. I'm glad actually people do it. There's a lot of things there which is really quite interesting. Because actually, that's where we got the hint to try to do this, okay? So, again, my little cartoon model and knowledge. Now, what I want is a machine. I want to build a machine to actually find the perceptual laws, and that would be K, not raw. Before, sort of I built a machine, the speech recognition experiment, I built a machine to actually had one parameter. I only vary one parameter, this resampling parameter new, and I was able to do the experiments that showed improvement. Now I want K. I want to find actually the whole curve. I want you to give me the whole function, this Mel scale function. Can I discover the Mel scale function from data? Again, every 10 years I go to a workshop, or every 5, I mean, that was 1997. Actually, I was the leader of the group, and again, similar with Terry Kam and Hinek Hermansky, everybody started laughing at us, say, you're going to do this, you don't have anything better to do here, this is really totally nonsense, blah, 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 blah. I say, well, remember last time we had a crazy idea, and you told us the same thing. So we went on and did the experiment, and here is the experiment we did. Before I go on, let me describe a little bit of the front end. This is a busy figure. I want you to concentrate on this. This is a typical state-of-the-art acoustic front end that is used in state-of-the-art speech recognition systems. It starts with speech. You take 256 samples. You do an FFT, and you use a Hanning window of 2.5 frames. An FFT, you take the real part of the FFT, you get basically 128 samples. You throw away face. So you get 128 numbers now. And you're going to give these numbers to your HMMs. Before you go and do things with the numbers, it's too many numbers. I don't want to have 120 numbers every frame. I want less numbers. So what we're going to use is on the Mel scale mapping. Mel scale says we can get equally spaced frequency bins and compress them so we can get smaller bins. So we actually use a Mel scale, and we take the 128 numbers and get basically 24 numbers. And what we want to do, we're going to get more numbers, more linearly spaced frequency bins for the low frequencies and logarithmically scaled bins for the high frequencies. Do you guys follow this? So this is really, think of it as a Mel scale as something that takes a lot of numbers and produces fewer numbers, okay? You compress, you lose information, okay? Now, so what we want to actually find is, instead of using this Mel scale that everybody uses, everybody says, oh, we do Mel scale, capture coefficients, and writes the paper and move on. We want to say, well, let's find out, not the Mel scale, let's find the right scale for a given problem. So I want this mapping from 128 to 24. And the way I'm going to find that mapping is through data. So, because we know we can normalize, we proved that 1994 we could do that. Is this normalization, is Mel scale, first of all, the best thing? And second, is this linear warping that we did? Remember we rescaled the frequency spectrum by a factor of 0.1, 0.2, 0.3. Is this the best thing to do? Maybe not. Maybe you should do a nonlinear mapping, I mean, let's do something better. So this is really the reason why we did the experiment. What we did, we said the following. We're going to take a database. This is the Michigan vowel database. It's 12 vowels, H, vowel D, hard, head, hard, basically individual speakers saying this, vocalizing the H, vowel D phrase. We have 45 males, 48 females, okay? So we have actually a lot of people now, 100 people in this database. And what we did, we said, okay, let's make a machine now. We split the data into training and testing corpora. Let's make a machine now to really do recognition of the articulation for each segment of speech, okay? And in fact, let's parameterize the machine now. So we basically built a very simple maximum likelihood recognizer. Very simple idea. I mean, very, very simple. But we built 1 million recognizers, okay? Each recognizer now with a different parameterization of the Mel scale. And basically, we say we have n numbers to start with, 128. We want m numbers at the end. These are the output of the Mel scale that we're going to invent. And what we want to do, actually, we want to group the channels in such a way that as we go to higher frequency, we incorporate more channels in the grouping, okay? We use, let's say, 1, 1, 1, 1, 2, 3, for example. So the total number of channels is n, where the n is the number of channels. So, for example, if we had n equals 8 and m equals 5, only n input spectral beams and 5 output spectral beams for our Bell scale, then we'll use linear at the beginning, 1, 1, 1, and then just put everything else at the last 5 in one beam. Or we could do 1, 2, and 4, or 1, 2, 2, and 3, and so on. You know, different parameterization, different binning of the frequency beams coming from your FFT system. Okay. So we did that, and in fact, for the sake of concreteness, to be concrete, we actually started with 118 samples for the input spectrum, and we produced an output spectrum, the Mel scale output, so to speak, 16 channels. And these are really, so we actually built 845,000 recognizers, okay? And we're running these maximum likelihood experiments for basically 6 weeks on 6 parks. People were pissed because we're using all the machines to really do this experiment. It's kind of a brute force approach to actually find the optimum filter bank. But after running these recognizers, and when all is said and done, we basically get typical warpings, typical, I mean, this is actually typical warpings that we got. You know, you can see, for example, we have a linear warping, and then we have a linear and then saturates, and then we have something that will look like a Bell scale. And guess what? After we've done the experiment, and we look at the warpings on both males and females, we pick up now the bottom 1,000 warpings in performance, which recognizer was the worst recognizer, and the worst 1,000 recognizers use these warpings here. That's not very interesting. And the top 100 warpings are these here. And if I put now my top 32 warpings for males and females, and I superimpose the Mel scale, you can see now that my best 32 transformations of the spectrum got something that is very close to the Mel scale. Now we said, and I believe it or not, I lost this data. I have to find the hard copy for this. But now we said, we're not really happy. This is really amazing, actually, because we did discover the psychophysical scale for perception, you know, at least, you know, based on this idea of which machine should do as good in decoding this data. So now we say, wow, this is not really, it's good, but there's a catch here. So we actually then split male and female. And we look now for the best warpings for the males and for the best warpings for the females. And what's happening actually, I don't have the data here, but the best warpings for the male just right for the males just fell right smack in the middle of our best warpings. And what about the females? The females, actually, the best warpings for the females actually were more linear. So yes, we're finishing up.
Yeah, I've got to get the next speaker needs some time to set up.
I know. I thought we had it. What time is it, Andrew?
About
5:02. Yeah. So I'm finishing up. Yes. So the point to be made is that the Mel scale actually is for males. That's why it's called Mel scale, you know, and the female scale is actually more linear scale, something that actually, I mean, is really an interesting experiment, an interesting result that was really found from the data. Okay, I think that was the last slide. These are some good references books for speech and voice communication, and of course, transactional signal processing. Acoustical Society of American Speech Communication are really top journals for things in this area. I hope you learned something today.